Time to think about how my entrance will be. So I'm exhausted, but nevertheless, I still want to address our approach to integrate compliance into a robotic leg by directly making the structure of the leg itself compliant. And we saw this a couple of times now, roboticists, we tend to look at nature, see muscles and tendons. They store and release elastic energy over the course of the gait cycle, so we want to do the same. We're copycats, and we came up with a very successful approach called series elastic actuators, which we also saw a couple of times. But from a design perspective, this seems kind of weird, because what we do is we build a rigid robot, we make it from metal, we optimize the structure to be as lightweight as possible, but it's still rigid. And then we artificially introduce elasticity into the design of the robot by adding springs to the actuator. Whereas we could do the other way around and directly making the structure compliant. This is what I'm proposing here. I turn the shank of our robot into a spring. And then I connect it to a set of rigid bodies which are actuators, so I call them the actuator. And now instead of controlling joint torques by spring deflection, I want to control contact forces by deflecting the spring down there. And in order to get our design to work, we identified a couple of challenges, plenty of challenges, like there are three major ones, which is how do we model such a system, how do we control it, and what do we do about a sensing problem. Due to time constraints, I can't go into details about modeling and control, so just to show you some results of our force controller, which is able to track desired reference trajectories which we can predefine and give them. Doesn't really have to look like something that appears in locomotion, it's an actuator, we can command steps. We can also disturb our system. This is me on the first experiment where we tried this controller. I was rather wary if my hand's getting crushed, so not disturbing too much. But we could still hold some constant forces while disturbing the system. And then lastly, we achieved squatting by just using our force controller and then on top virtual model control. Perfect, I'm done with my PhD, except there's a time issue. So far, we have to rely on an external force torque sensor for our control to work. And in our test bench, perfect, no problem. But outside of test benches, and we are talking about locomotion, we want to move forward, we can't use that. So we have to find a way to get rid of this external force torque sensors, and that's what I'm talking about. And the first idea that I had is, hey, we could just integrate our force sensor directly into the knee. I built it and then realized, wait, we propose a lightweight leg design, and then we add around 500 grams of mass to this design by just adding one simple sensor. That's not good. So instead, we came up with strain gauges. And I did not know where to place them, so we just had an intuition that we want to place strain gauges to maximize lever arms. So here's how it works. If we have a pure horizontal force acting at our weird foot down here, maximal lever arm points to somewhere up there. So we should place a strain gauge up there. If we have a pure vertical force, the lever arm is pointing to someone outside for this shape assembly. Note that in our setup, we cannot put this first strain gauge up there because that's where we attach our actuator to. So we close it as close as possible to this position. And with the setup, we use an industrial mill here, change relative position of the adapter to the foot, and measure strain gauges and forces. And since these quantities do seem kind of good looking in the mean, we are now working towards, and we actually do stuff with that and estimate contact forces. Currently, very preliminary, only works in a really simple simulation, but rephrase this equation to get an ODE, take it as a prediction step in the Kalman filter. Whenever there's a measurement, update your prediction, and then use this expression down here to compute your contact forces. as I said, it's simulation and simulation. Everything works, so this works. And with this being said, I'm at the end of my talk. Almost. Thanks to my supervisor David, thanks to my student who's not here, thanks to our funding source, and as part of the SEA called ChatGPT helped me come up with a limerick. And I'm not gonna read this out. It's yours.
So just to put a fine point on, like, what philosophically separates you from like the Rex robots? I mean, I see the Rex sea legs. Is it the active control?
So Rex uses this kind of motion, whereas we don't use this kind of motion.
Yeah, I do frame this. Oh, let's put compliance in the structure.
Yep.
I imagine a lot of people here would agree with you on that. So, that's right.
No, wait. I think you were first.
Oh, sorry, I'm helping.
So strain gauges are sensitive to temperature. You had to what they imagine with the material properties.
And that's one of the main things why it's not working in hardware. They are sensitive to temperature. In this experiment, they burn, so I don't know why, but we'll see. Have to figure it out. So now it's tough.
So, speaking of Rex, Patreon back in 2003 put 2 strain gauges on a Rex leg to try to estimate the information of that. Are you familiar with that? Have you seen how we did? How does yours differ?
I'm not familiar with that particular research.
And do you feel, logically it seems like you'd want at least 2 strain gauges. If you wanted one, I would suggest you put it about 15% away from the hip, do the sort of rigid body model sort of kinematics, but I suspect that you're going to want 2 in order to capture the reflections on this.
Yeah, I think one is good enough if you just want to have like an estimate for the end effective positions of the foot, and then you just use your statics and identify some spring stiffness and help compute from that. But yes, right now I want to have 2. I don't know who's next.
So, can you comment on why you specifically use those sensors apart from other possible approaches? For example, you could also measure reflection of the foot tip, for example.
Perfect, great question. So what I tried to do is include a laser sensor to get an estimation of the deflection of the foot, but it deflects in 2 dimensions. And then at some point you have a good estimate, and at some point you don't. So you would have
also have 2 sensors.
Yeah, sure. So it's still, it's just a different.
Okay.
And I'm way too close to the camera.
Comment on the temperature curve. Yes, they drift. Probably you didn't have a huge change in temperature, but the drift is linear. So if you had a temperature, you could take that into account. And to the amount of strain gauges that you want to use, I believe the name is Whitestone Bridge. So you can put them in an arrangement so that they cancel each other's certain properties. So you also have less probability variation between one strain gauge and the other one, and that stuff. So that was something to do.
Thanks for coming. And thanks to y'all